All right, the other version of the Clausius-Clapeyron, or Clapeyron, I say Clapeyron. Who really knows? It's like trying to say Louis de Broglie, like, who knows how to say it? Is the linear format where all that's been done is the natural log of both sides has been taken in order to undo the exponent of the natural number e. Okay, you take the natural log of both sides. So when you do that and then you arrange it in this particular way, you get an equation of a linear line, don't you? Y equals mx plus b. So using this information, I can give you a graph like I did on the next in-class example. And if I give you the equation of the line, where you have the slope and you have the y-intercept, you can figure out t or p. You can figure out y or x. Okay, so let's look at this example I gave you guys. Notice on the y-axis, what is on the y-axis in this situation? Is it just pressure or is it the natural log of pressure? It is absolutely the natural log of the pressure. What is on the x-axis? Is it just temperature or is it 1 over the temperature? And so the units down here are not Kelvin, they're inverse Kelvin, right? Okay, we just got to keep in mind what we're actually working with, okay? All right, so here's the graph. And really the only piece of information you actually need to be given is the equation of the line. Y equals mx plus b. What number is this? Is this 9? Y equals what? Negative 3759.3 x plus 18.928. Okay. That's really all the information you need. From here, I would say you need to for sure understand if it tells you your graph is the what? Natural log of pressure versus 1 over T. You guys need to understand now that that is talking about whose equation? The Clausius-Clapeyron equation. If you're told a graph of natural log of vapor pressure versus 1 over the temperature, guys, that means you're dealing with the Clausius-Clapeyron equation. Because that equation is about the relationship between pressure and temperature. It's this. What is this R? What does our slope value represent? What is M equal to? Negative delta H of vaporization divided by R. What is B equal to? What is this y-intercept in my equation equal to? That's what I need you guys to really understand. Okay, so that's the y-intercept. That is equal not to A, right? It's the natural log of A. B is this value. Okay. What did I ask you to solve for? Determine delta H of vaporization and A for this substance in this graph. The relationship between pressure and temperature, when we take the natural log of it, We should always be able to figure out this consistent value of delta H. If we know the slope, we can get that value. I can get the value of A, which, what was A again? A is just some constant value for that substance. It actually has to do with how many collisions it does, but we're not ready to talk about that yet. Okay. But so what's delta H? How do we find that? How do I find delta H? What algebra am I doing to find delta H? What does this actually equal? It equals this number negative what? 3,759.3. Okay. Solve for delta H. Do some algebra, solve for delta H. What is R? 8.314 or 8.314 times 10 to the negative third to get the answer in kilojoules. That one. So the negative sign would cancel itself out, right? If you have a negative on this side and a negative on this side, then those. You mean right here? Yes, the negative sign is part of the equation. Yes, yes, yes. But the slope of this graph should always be a negative number. So how do you solve for delta H of vaporization? You really just got to do R times 3,759.3, right? That's it. That's what you got to do. Which is what? That sounds about right. Everybody understands why the negative sign is gone, right? Cancels there, cancels there. How many sig figs should this answer have? Well, the version of R that I'm asking you guys to use has 4 sig figs in it. It could have more. I mean, it can go at, this is not an exact number. It can have more. So 4, that has 5, which means our answer, let's round it to have 4 sig figs. So 31.25. And then what should be the units here? What are the units of delta H? Kilojoules per mole is what enthalpy units are. Kilojoules per mole. Okay. How are you going to find A? There is stuff. How are you going to find A? How do you undo a natural log? Okay. If natural log of A is equal to whatever my y-intercept is, so it's equal to 18.928. The way you undo a natural log is base E. Both sides are now raised as a power of that natural number E. When you raise a natural log exponent with E, that is how that is undone. That is how those two operations mathematically cancel each other out. So you get now just A. Just A. This comes down here into the main body of the problem. This is just A now. If you need to review how to manipulate natural logs and things, I think I've got a source somewhere on how to do that. Maybe. Yes, it should be a huge number. Huge. So now you're doing in your calculator e raised to the 18.928. Remember, you got to use that natural number e. You got to find that button on your calculator. That natural e raised to. I think it's supposed to have. This is supposed to have 5 sig figs. Here's how I know that. Wait a minute. Is that what I said? Actually, sorry, excuse me. This isn't supposed to have. This really is supposed to have 3 sig figs. Here's why. I have it wrong on my slide. It's supposed to be 3 sig figs. Here's why. Anytime you're doing logarithms and exponents and you're working with sig figs, this may be a brand new rule to you guys. I don't necessarily have expected you to know this, okay? Okay. Whatever your exponent number is, count how many places past the decimal it went. Whatever your exponent is, count how many decimal places past the decimal it went. And that is how many sig figs your answer should have. Okay. We'll get a lot more practice with that when we get to our acid-base chapter and we start calculating pH and stuff. It'll be necessary there. But so what should this answer been round to? I guess 1.66 times 10 times 10 to the 8. Yes, huge. Does this have units? No. A doesn't have units. No units. Okay. No units. Let's try a different form of the Clausius-Clapeyron. Let's try the 2-point form. So you guys should see that on your sheet. You guys see the 2-point form on your useful study sheet? Two-point form of the Clausius-Clapeyron equation is useful when you're not given a graph to look at and you're not given the value of A to calculate using the original Clausius-Clapeyron equation. 2-point format should be used when you are given what? 2 data points, 2 data sets. Specifically, what kind of 2 data sets? What are the 2 things we're comparing with Clausius-Clapeyron equation? Pressure and temperature. Use 2-point when you're given 2 pressure, or it doesn't really matter. It's actually XY. So 2 temperature pressure data sets. Right? Let's try one. Look at 10. Carbon tetrachloride has a vapor pressure of 54.0 kPa at 57.8 degrees C. Okay. That's how I always do my problems, guys. Let's start writing down what I was given. I was told a pressure of 54.0 kilopascals. At a temperature 57.8 degrees C. Anytime we are working with gases, vapor, whatever, we're working with gases, guys, what is the temperature scale we have to be in? Kelvin, never Celsius for gases, never, never, never. So very first thing is you better just go ahead and change that temperature to Kelvin. Which is what? 330.95 Kelvin is that temperature. And I would mark to myself where my last decimal place was, because that's informing how many sig figs that answer represents going forward. Right? For my temperature, went to the 10th place, and I added this number to it. And so now this number is significant also to the 10th place. I don't round any of my numbers until the end. I never have. I never do. For these Gen Chem 1 calculations, if you rounded right here and you used what number instead? 331.0 to the 10th place. You're going to get the same answer I am. It's not going to make a huge difference. But as best practice, why would you round now? Just wait till the end. What do you want to call this data set? This is a pressure and temperature that go together. Maybe I'll call them one. Let's see if that's the best choice for me. Let's see. But they go together, don't they? This pressure and this temperature are a set. So whatever number you decide to give them, it's got to be the same number. What else am I going to tell? Okay, what is the normal boiling point? So you guys got to understand now, what is that actually asking? What is the normal boiling point? Am I looking for a pressure, or am I looking for a temperature if I ask what is the boiling point? I'm looking for a temperature. What does that word, let's say that this is my second set, what does that word normal mean to us? Standard temperature. Standard pressure. What unit should I use? Because I already am using that unit over here. So what is standard kilopascals? 101.3. Excellent. And so this is asking for my temperature in degrees C, but guys, does that mean that I'm solving my math in degrees C? Never. It's Kelvin, and then you change at the end. In order to use Clausius-Clapeyron, dealing with pressures and temperatures, I need the pressures, I need temperatures, I'm solving for one. What's the other thing I have to be told? The vaporization, the enthalpy of vaporization. And now is where the algebra prereq comes into this class. Now is where the algebra prereq comes in. Because you guys have to rearrange this equation and solve for what variable? That guy right there on the bottom of this fraction. I have a trick. I have a kind of shortcut. It's not really a shortcut. It's still the same amount of work, but what time is it? I'll just give you a minute. Let me just see if y'all can rearrange that. And then I'll share with you my little trick if you want. And if you have a calculator that is set up for you to type in all these numbers and just leave that as your X or whatever it does. All I'll say is this. That's fine. However, I've seen before, if you don't enter it in your calculator right, then you get the wrong answer. And then guess what? I can't give you on a problem. Partial credit. Because your partial credit on a show your work problem like this is going to be some of you showing me that you can rearrange this equation. That's part of it. So if you just are trying to just spit it into your calculator and just get the number out, that might be fine sometimes. Sometimes you'll get the wrong answer, but you definitely won't be getting partial credit for it. So. Y'all ready to show you? Y'all ready for me to show you what I got when I rearranged it? Let me think for a second. That's what you got too? Yeah, girl. Y'all see how I did that? Did I go too fast? So remember, when I rearranged to this point, I had 1 over T2. That's the inverse. In order to have just T2, I have to take the inverse of both sides. Okay, do y'all want to see my little trick? Since we're basically out of time, so I'm not gonna get to show you this stuff that I was wanting to show you today. So that's fine. You want me to show you my trick? Okay, let's do that. I'm gonna leave this here. Let me come back to where we started from. Okay, this is what I do sometimes. Actually, honest to goodness, this is what I'm doing in my head. I just can do it in my head and I don't write it down. Okay. Why don't you think about it like this? Let's let this whole quantity right here, just call it something easy. A. There's A. There's A. Let's just let this whole little quantity right here be something easy like B, just for the letter's sake. And then let's let this whole thing right here be the letter C. Now, try to get C by itself. Why? Because C is where my T2 is at. So let's just isolate C. What do you do to isolate C? Divide both sides by B, right? Okay. So let me come over here. Is it okay if I just put C on this side of the arrow because that's equation, because that's the way I like for it to look? Okay. C equals what? A divided by B. Everybody with me so far? Okay. So now let me plug back in what I let C represent. Let me just plug back in what I let C represent. C represented for me what? 1 over T1 minus 1 over T2. And that is equal to whatever A equals divided by whatever B equals, right? Okay, I still want to get T2 by itself. So what do I do now? I would add, I mean, the way I see it is I would add 1 over T2 to both sides. Or you can think of it, there's a couple of different ways you can do this. And then I would do this minus this. No, never mind. That's fine. That's just the way my brain sees it. Come on. Let me do something different. I mean, you're going to get to the same thing either way. But why don't we do this? Let's just do this. I want to do this. Okay. So let me subtract 1 over T1. Right? That'll cancel that out. Want it? Yeah. Now what do I have? Negative 1 over T2 A over B minus 1 over T1. Okay. I don't like that that negative sign is there. So what am I going to do? I'm going to multiply both sides by -1. Let's do that. So what do I have now? Negative A over B. What? Plus 1 over T1. Okay. And then the last thing is that this is still on the bottom of this fraction. I don't want the inverse value of 1 over T2. I just want T2, which means I have to do what to both sides? Raise it to the power of -1. Right. So really all I did was not write the individual symbols for what I call the A and B. If that helps you manipulate around more, wonderful. But you still got to be able to do some algebra, right? Okay. Here's the answer. So then you got to go plug it all in, right? And I'm going to put the answer up here, and I'm going to let you guys just tell me that, yeah, that's the answer. Wait a minute, where's my answer? Here it is. Okay. What unit is my temperature going to be in? When I plug it all in and I do all the math, it's going to come out in Kelvin. When you do the math, you should get 349. And then I got 0.2. If your answer is a little bit different from this because of rounding or something, that's fine. And then you need to do what to get the final answer? Let's subtract 273.15, and that'll give a Celsius temperature of this liquid. Its normal boiling point under standard pressure of 76.1 degrees C. Yeah. We'll have to go through the plugging it in your calculator together then. I'm telling you that you and I will have to go through it together, because that's the answer. So we will not be able to work every other example I have of this Clausius-Clapeyron 2.4. We just don't have time. There's 2 more in-class examples here. 2 more. That was number 10. We've got number 11 and number 12. 11 and 12. Both also use the Clausius-Clapeyron 2-point equation. Solving for a couple of different things. One of them you're solving for delta H. The other one you're solving for a pressure. We practice solving for a temperature, okay? Guys, you need to go through these two examples with these slides. Just like if we had we have a textbook. But just like if we had a textbook and I told you, look at examples 10.12 and 10.13. That's this. That's me telling you to look at the slides, okay? And then tomorrow, we got to cover the next topic. But if any of you are having problems with the algebra of it, with the rearranging of it, let's get with me tomorrow and let's go through it together during a little bit of downtime we're going to have during lab tomorrow, okay? Okay. Or hell, if we got downtime today, if you want to ask me today, that's fine too. But I'm putting it on you guys now. Examples 11 and 12. They're in the slides. Let me make sure I got the solutions in the slide before I say all that. I'm pretty sure I do. Let's just double check. Clausius-Clapeyron 2-point. There's the stuff. There's the rearrangement. Yeah, okay. And that is indeed actually the end. These last two examples are the end of the lecture 1 slides, okay? That's where we're finishing that now. That's done. And tomorrow we're going to start the second set of slides. So questions? The algebra can be hard. I mean, it's just a lot of letters to keep up. Plus, we got this natural log function in there as well. You just got to keep track of a lot of stuff. Okay. Is this what we would have expected this pressure to do? I mean, this temperature to do? At this pressure, there's its boiling point. Or there's its temperature and there's its vapor pressure, right? Boiling point is specifically when it's equal to what? The atmospheric pressure. Okay. So, but here's normal atmospheric pressure, and the temperature is greater. 76.1 is greater than 57.8. Does that make sense? Less pressure, lower temperature, higher pressure, higher temperature. Yes, that should make sense. If you got a number that was negative temperature, you'd be like, no, something's not right there. Something's not right. Okay. Did I scare y'all with the algebra? Robert. Okay. Practice, 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 practice. All right. Let's go. Let's take a break. Let's go to lab. You guys are going to finish your titration lab today. You're going to still use that same base solution that you standardized yesterday. I would love it if each group would write up on the whiteboard your average molarity that you calculated yesterday. And then I want us as a class, I'm going to average them all together. And that's the value we'll use for today. I like that. Let's do that. Because I think we're going to come out around 0.15-ish, which sounds good when we average. So.